Hello everyone, this is my second special, Insane Geometric Proofs. My first one was about infinite arithmetic series, and I did a short version on that too. So if you're interested in math and that's why you clicked on this video, you should probably go check one of them out. If you want to watch it in 30 minutes, a full detailed explanation, go to the special one. If you want to watch it in 7 minutes, just short, just to get the main idea, you can watch it, the short version of it. Now, I'll explain what I mean by the title, Insane Geometric Proofs, and All Triangles Are Equilateral in a few minutes. But first, I wanted to quickly announce, for those of you who didn't watch my short version of the first special, I'm switching to yellow color instead of blue. That's mainly because it's a bit harder to see with blue. Now, another thing I wanted to say, I would greatly appreciate it if you could subscribe to my channel if you haven't already. As you can see, 0.5% of my viewers have subscribed, and that is pretty low. Now, if you don't want to subscribe, if you just want to watch for fun, I'm completely fine with that. But if you think this content is interesting and you could really use some help, subscribing will help you get notifications that I made a new video, or basically it'll help you in general. So if you wouldn't mind, just click the subscribe button. If not, then that's fine too. This is mainly a free channel if you want, if you would like to say that. Now, let's talk about our actual video. Enough of the intro. You're probably wondering why I named it All Triangles Are Equilateral, and probably why I called it Insane Geometric Proofs. Well, the reason they're called Insane Geometric Proofs, if you remember back to my first special, I gave you a proof that seemed insane, but was actually, it had actually some certainty to it. You could prove it, and then you could actually understand. Of course, it's not taught in high schools because it's not regarded to be true, but you could prove it technically. Now, this is completely different. It looks normal, like what you do to it looks normal, but the result is astonishing. For example, all triangles are equilateral. There are many examples of this, like pi is equal to 4, but I'm going to be talking about the funniest one, all triangles are equilateral. Obviously, if you've taken geometry, you'd be thinking, of course not all triangles are equilateral. I can even draw this triangle, and that is obviously not equilateral, is it? Now, let's just take this triangle. I'll show you the insane proof through this triangle. Note that this proof is not true. That's the main difference between this and the first special. In the first special, it was true and everything was fine. In this special, I want to show you how I can prove something false to be true by making one tiny inaccuracy. Basically, out of everything, only one thing is inaccurate, and it's a very subtle thing. It's probably the most subtle error in a proof. So I'd like you to see if you can catch the error, actually. For those of you who are up to a challenge, see if you can catch the error. So first I'll go through the proof, and then I'll explain you what the error is. So let's get right into it. So the first thing I want to show you is, let's draw the perpendicular bisector of this side. The perpendicular bisector, for those of you who haven't taken geometry or seen my geometry series, I have a channel for geometry, and one of the videos is about triangles. In it, I talk about perpendicular bisectors and everything else, like angle bisectors, which we'll also be talking about in this proof. Anyway, back to this. Let's draw the perpendicular bisector. That's basically a segment that's perpendicular to the side of the triangle, and it also splits the side exactly in half. So these sides are equal or congruent. Now, let's also draw the angle bisector, like I said. If we draw it like this, we want to find out where it intersects. So let's say this point is P, and these two angles are congruent. Yeah, these two angles are congruent. Now, one thing we want to do, we can do anything we want here, but the thing I'm going to show you, the proof of why all triangles are equilateral, is you draw the segment that's perpendicular to the other two sides. So we have this triangle. I'm going to use a different color for this. Ooh, pink. Pink is nice. These two triangles. And then let me also draw another two segments that creates, that creates some more triangles. As you can see, I'm really good at drawing geometrical figures, huh? So that's this triangle and this triangle. And then last but not least, this triangle and this triangle. Sorry if it's a bit messy. I'm trying to draw this in a way that it's easier to understand. That's why it's sort of messy. I'm sort of hurrying it. Now, let's talk about the pink triangles first. The pink triangles, we can prove that they're congruent. Congruent triangles basically have a set of rules. They basically are identical. So how can we prove that? Well, one rule we can do is sides. I'm going to use yet another color for this. This brown side is basically equal to itself because, well, it's equal to itself. And then the right angle is also equal to itself, if you can see that. And finally, we know that this angle is also equal to that. So now we have AAS. AAS meaning angle, angle, side. So one right angle is equal to another, basically equal to itself. One angle is equal to the other, equal to itself. And one side is equal to basically the same exact side because it's the same thing. So that's one criterion for proving that it's congruent. Let's talk about the other ones. The blue triangles will come to last. Let's talk about the green ones. So we know this is congruent to that. Sorry, wrong pair of sides. This is congruent to this because it's a perpendicular bisector. This is congruent to itself, like we did in the example above. And then we know that these are right angles because it's a perpendicular bisector. So now we have SAS. And that's also a valid rule. So the mistake isn't about the congruency of triangles in this case. It's about something else that I'll explain later. And finally, we have this triangle. So how do we prove it? All we know that these angles are both right, so they're congruent. We don't know anything else, literally. But we can use the fact that the pink triangles are congruent and say that these sides in return are congruent because corresponding parts of congruent triangles are congruent. That's a rule that says that if you have two parts that are corresponding of congruent triangles, they are congruent. So given that, we know these two are congruent, and we also know that these two are congruent because of the green triangle's congruency. So yes, this looks very messy right now, but if you can follow along, we're almost done. We're basically saying that these two are congruent, meaning that it's hypotenuse and a leg of a right triangle are congruent. And that's also a valid theorem. Hypotenuse and leg of right triangles are congruent. So now we know all of this. We can use CPCTC, this theorem, one more time. And we can say, one more new color, let's see. Red seems nice. We can say that this is congruent to this. So now, given that, we know this is congruent to this because of CPCTC, and we know this is congruent to this because of CPCTC. So this plus this, let's say it's 1 and 2, 1 and 2. 1 plus 2 is equal to 1 plus 2, meaning that this entire side length is equal to this entire side length, meaning the triangle is isosceles. Two of the side lengths are the same. But you might be thinking, well, wait, this is isosceles, not equilateral. So how is it equilateral? Well, we didn't make any specifications. Both are generalized. They both can be any two sides, meaning any two sides of the triangle are congruent. So these two sides of this triangle are congruent. And you can also prove that these two sides are congruent and these two sides are congruent the same way, meaning all the sides are congruent, so it's equilateral. Meaning I'll just turn this into a red line down here. So now all the sides are congruent, meaning it's equilateral. So how do we do this? Like, the proof is there and everything looks reasonable, doesn't it? All the theorems we use, the rules we use, they're all valid. So where's the mistake? Pause if you want to figure it out. Okay. If you have figured it out, congratulations. It's a very subtle mistake. But for those of you who haven't, this mistake is, let me erase this so I have more space. The mistake is when we first drew the diagram. I'm going to go back to yellow and draw this. Perpendicular bisector, we got that. But the mistake was with the angle bisector. I just roughly drew it on purpose. I roughly drew it like this. But as you can see, these two angles aren't equivalent. They're different. The actual angle bisector goes like this. And you might be thinking, then what's the difference? The difference is that it intersects outside the triangle. This even is not the actual angle bisector. It's a bit different, but it actually intersects outside. So the congruence and everything would still be there, except now we don't have the congruence of these two sides. We just know that these two sides are congruent. Oh, sorry, I have to do 3 ticks for this, because like every side has to have different ticks. This has 1, 2, that has 3, which is why I made 4 ticks over here. Anyway, we can't tell that this is congruent to this. All we know is that this is congruent to this. So the proof doesn't really work. The proof only works if the angle bisector meets the perpendicular bisector inside. And that, by definition, is an equilateral triangle. If you like this type of video, like I said with the first special, please leave it in the comments and maybe even ideas of what to do next. I'd really appreciate one comment even about how I'm doing, because I don't know if the audience likes this. But with all said and done, I'll continue making videos like this. See you later.